Hello. Today we shall be speaking about what is called indeterminate quantities. And indeterminate quantities, they are quantities that appear associated with the subject of limits. And why we call them indeterminate? Because they can assume really any value. And there are 7 of them. So first of all, we shall we shall be exposing these indeterminate forms and their types. Then we shall be mentioning a theorem after Cauchy, and this theorem, it's the one to prove another preceding theorem, which is very popular for students. They can use it to calculate limits better than the ways or the classical ways that we have exposed. And then we shall also explain some behavior of functions, like, for example, how we can associate with functions the property of either it's an increasing function or it's a decreasing function, etc. And then this is again a property of functions called concavity or convexity, and we shall speak also of inflection points. I mean, in other words, this is really, it's not one subject we shall be dealing with, but first of all, we shall speak of indeterminate quantities. Now, for indeterminate, what are the indeterminate forms? Now, when you say, for example, 0 multiplied by 0 is equal to 5 multiplied by 0 is equal to square root of 3 times 0 is equal to minus 1 times 0, all of that, all of these quantities are equal to 0. You can algebraically say, then in this case, 5 divided by 0 is equal to square root of 3 divided by 5, because all of them actually are 0 over 0. In other words, your 0 over 0 becomes equal to minus 1 over square root of 3, and it can be also square root of 3 by 5, divided by 5. So there is no definite value for this quotient, which is 0 over 0. So we call 0 over 0 is an indeterminate quantity. Now, these types of indeterminate quantities, we list them here because there are 7 of them. I mean, they appear associated, as I said, with the subject of limits. Why they are associated with the subject of limits, and where do they appear? For example, when you try to obtain the limit of a function, we said before here, for example, here, you wish to calculate the limit of you wish to calculate the derivative of a function f at the point A. What you do is that you take the limit of this quotient. Now, this quotient here, you find that the denominator tends to 0 when x tends to A, and the numerator also tends to 0. Why? Because the function is continuous. Because we said before that a continuous function, a differentiable function, in order that the derivative exists, it must first of all be continuous. So from the condition of continuity, which must be imposed first, you have that the limit of f of x when x tends to A is equal to f of A, and therefore here you have the denominator and the denominator simultaneously, they approach 0. So you have a quantity 0 over 0, and we don't know really the value of the derivative. So this is one case or situation in which this type of indeterminate quantities appear. But it's not the same, in fact. You can have also infinity over infinity, or infinity minus infinity, infinity times 0, and 1 to the power infinity, and 0 to the power 0, and infinity to the power 0. In other words, these are 7 most important or indeterminate forms that you encounter all the time when you are taking the limit of a certain expression, and you fail to find the definite value of this expression because you end up with one of these indeterminate forms. So the idea is to find, when you take the limit, the idea is to find the precise value of this limit by violating through a detour how you can get rid of the quotient 0 over 0. Now, to do this, as I said, these are forms in which the indeterminate form appears. This one that we just viewed is that here you have a function in which you want to calculate the derivative of f at the point A, so you take the limit of this expression. So the denominator tends to 0 when x tends to A, and as well, the numerator also tends to 0 because f is continuous at A, and you end up here with 0 over 0. Here, this is the expression by which you calculate the number E. Because when you take the limit when n tends to infinity, you obtain the number E, which is Euler number. Again, when you do the first limit, the first operation of limit, you obtain 1 to the power n when n tends to infinity, so you get the first one of the indeterminate quantity, 1 to the power infinity. So any of these indeterminate quantities, they appear usually associated with the subject of limits. When you take, in the first step, you take the limit and you are stuck with one of these indeterminate quantities. Now, in order to get rid of this indeterminate quantity, you have to find a way, you have to rely on a theorem called L'Hopital. In fact, L'Hopital was a French mathematician from an aristocratic family, because his name is de L'Hopital, and Guillaume de L'Hopital. He was a contemporary to the beginning of the 18th century at the time, and his tutor was Bernoulli. Bernoulli, as we said before, is not one Bernoulli. When you read in literature Bernoulli, there are a series of a family of 12 Bernoullis. They work in different fields of mathematics and physics and statistics. So this L'Hopital, actually the theorem is not his, it's of Bernoulli, but because he is the first one to have written a text on calculus, and this is why it's attributed to him. But the rigorous proof of L'Hopital, it wasn't by him. It was almost later, a century later, by a French mathematician called Cauchy. Cauchy is the father of modern analysis in our modern times, because he's the one to have proved L'Hopital rule. He's the one to have proved Taylor expansion on a rigorous basis. He's the one to have introduced the improper integrals. He's the one to have extended the fundamental theorem of Newton, because Newton theorem, which is the fundamental theorem of Newton and Leibniz, didn't discover calculus, but they discovered the fundamental theorem, although it was only applied to continuous function, but he could extend it also to functions that have only antiderivatives. So actually he has contributed a lot of theorems and a lot of concepts in mathematics. So what Cauchy have arrived to, he has arrived at a theorem called Cauchy mean value theorem, and in fact he's the one to have also proved the first mean value theorem of our last lecture. Now this Cauchy mean value theorem tells you the following: if f and g are continuous on the closed interval AB and differentiable on open interval AB, and if g dash of x is not equal to 0 for all x in the open interval AB, then there exists a number zeta in AB such that this holds. Here the quotient of fb minus f of a divided by g of b minus ga is equal to f dash of zeta divided by g dash of zeta. Now what you can do, in fact, is that this, it looks very much similar to the mean value theorem we explained in our last lecture. Why? Because there we found that f of b minus f of a is equal to what? Is equal to b minus a times f dash of zeta. And also g of b minus g of a, you can also say that's equal to b minus a times g dash of zeta. But there, you cannot do this here. Why? Because here the denominator would be f dash of zeta 1, because you're not sure that zeta 1 is equal to zeta 2. So actually you cannot use our mean value theorem, the last one, to prove this quotient or this expression here. But what Cauchy did, in fact, is that he used Rolle theorem again, like the one that he used before to prove the first mean value theorem. You have here f of b minus f of a times g of x, and he subtracted from this g of b minus g of a times f of x. Now, we said before that if you use Rolle theorem, and if you have a function h of x that has two equal values at two different values, like for example, 2 different points, like for example a and b, then there must exist a point at which the derivative vanishes. We call this point zeta. So here, if you take the derivative, because you can, if you substitute x is equal to a, you find that h of a is equal, and you substitute again at b, you find that h of a is equal to f of b, and therefore there must exist a point zeta at which h dash of zeta equals 0. Now, if you differentiate this, you end up with this expression here on the slide, which is f of b minus f of a divided by g of b minus g of a. You get f dash of zeta by d dash of zeta. So you have one zeta which satisfies this mean value theorem. Now here also, we are not afraid that g of b is equal to g of a. Why? Because if g of b is equal to g of a, then according to Rolle, there must exist a point g dash, a point zeta at which dash vanishes. But g dash of x is not equal to 0, and therefore this denominator here is not equal to 0, and you get this Cauchy theorem. Now, from this Cauchy theorem here, mean value theorem, you can actually obtain directly the formula or the expression or the theorem the result of L'Hopital. How we can do this? Now, what we can do is that we can write it in the following form. Instead of writing f of a and f of b, you can write it in the form f of x minus f of a divided by g of x minus g of a is equal to f dash of zeta divided by g dash of zeta. Now, here, according to Cauchy, you have f and j are continuous on the closed interval ax, there it was ab, and differentiable in the open interval a and x. And this what we wrote actually here is our the theorem of Cauchy. And then you can set up f of x is equal to f of x minus f of a, and g of x, capital G of x, is equal to g of x minus g of a. Here, since both f and x, f and g, small f and g, are differentiable on ax and continuous on the closed interval x, so is capital F and capital G. Because if you take the limit, in fact, of this expression here, you got the limit of x when x tends to a from the right-hand side. This tends to 0 because f already is continuous on the closed interval ab. So in fact, what you have here, you have that capital F and capital J, both of them are continuous on ax and differentiable also on ax. And the limit and f of a is equal to g of a, both of them are equal to 0, and that the limit of capital F of x when x tends to a plus is equal to the limit of capital G of x when x tends to a plus, and both of them tend to 0 from the continuity of both capital F and capital G. Now we apply Cauchy mean value theorem. So you have here limit of capital F of x divided by G of x when x tends to a plus. Now, since both tend to 0, now we arrive at where the reason why you apply L'Hopital. You apply L'Hopital when you have the numerator and the denominator both tend to 0 simultaneously. Now, this both tends to 0, but there from Cauchy you get what? You get the limit when x tends to a plus to what? To f dash of zeta divided by g dash of zeta. But then, since zeta pertain to the interval from a to x, so when x tends to a plus, as if you said that zeta also tends to a plus. So what you have here now, you have the limit of f dash of zeta by g dash of zeta when zeta tends to a plus, as if you are writing limit x when x tends to a plus of f dash of x divided by g dash of x. And that's exactly L'Hopital. L'Hopital tells you that when you are stuck with the limit of the numerator and the denominator both simultaneously they approach 0, the numerator and the denominator simultaneously, then you can substitute this limit by the limit of the derivative of both capital F and capital J when x tends to a from the right-hand side, if you are dealing with an open interval from a to x. So all you have to you differentiate. Now the difference between this extension or this proof that we just did to prove L'Hopital rule is that L'Hopital rule you can have f and j, two functions differentiable on ab, except at the point c at which you seek, for example, to take the limit. So what we do, because to apply Cauchy mean value theorem, both f and j are continuous on the closed interval ax. So here you are not sure of that, or in any interior point to this interval. So what you do, you can introduce another function f prime, in which is equal to f of x when x is not equal to a, in which you are afraid to take the limit, and it's equal to 0 when x equal to a. Now the function f prime here is continuous on the closed interval from a to x, and therefore you can apply then in this case Cauchy mean value theorem, and you arrive at the same result. Now, since we have now proved L'Hopital rule, all you have to do now, we want to know what are the conditions under which L'Hopital rule exists. Now, we said here before that in order that Cauchy exists, both f and j are continuous on the closed interval ax and differentiable on the open interval from a to x, and the g dash of x does not vanish in any deleted neighborhood of the point c at which you take the limits, and at the same time they vanish simultaneously. And that's the most important thing. The most important thing is that when you take the limit, you find that both the numerator and the denominator, they either both tend to 0 or they tend to infinity. In other words, you cannot apply L'Hopital unless you are sure first that both tend to 0 or they both tend to infinity. So here is now the theorem of L'Hopital, that limit of f of x divided by g of x when x tends to c, any interior point at which both the numerator and denominator tends to 0, you can substitute this by the limit of the derivative of both the numerator and the denominator. But as I said, before you apply your theorem, you have to make sure that both tends to 0 over 0 or infinity over infinity. For example, you have here the case where f is equal to f of x, x plus 18, and g of x, 3x minus 2. Now, if you take the derivative, you apply the derivative, you get 1 over 3, which is wrong. Yet the limit, exact limit is equal to minus 9. All you have to do, you substitute x equal to 0 in both the numerator and denominator. Why is it wrong? Why here it doesn't work? Because you have to make sure first that both tend to 0 simultaneously, which you haven't done here, which you haven't found here. And therefore, this is wrong. You cannot differentiate before you take first the limit to make sure first that they both tends to 0 over 0 or infinity over infinity. Now, calculate the limit. Here, we have a function that when you take the limit of both the numerator and denominator, you have this tends to 0, when x tends to 1, and also this tends to 1. Now, we have to make sure first that now both tends to 0. Now, can we apply L'Hopital? Yes. Why? Because both f of x and g of x, they are differentiable in any deleted neighborhood of the point x is equal to 1, first of all, and the denominator does not vanish in this deleted neighborhood, and therefore you can apply, and both tend to 0 simultaneously. So now you can apply the theorem and substitute both f and g by f dash and g dash. So the limit there, you can differentiate the numerator, 3x squared minus 2 divided by 1, you get 1, and that's the limit, that's your limit. Again, calculate the limit of this expression here. Here, the quotient, again, tends to, when x tends to 0, you have a 1 plus 1 minus 2. This tends to 0, and this tends to 0. Can you apply L'Hopital? Then, in this case, yes, because you are sure that both tends to 0. And therefore, in the deleted neighborhood of the point x is equal to 0, here you get 1. But as I said, it's not g dash here, it's not equal to 0. In any of in the deleted neighborhood of this point at which you seek to determine your limit. And this is an interior point to any interval containing the point x equal to 0. And then, therefore, and since it is not equal, g dash is not equal to 0, which is the denominator, and both numerator and denominator, they tend to 0 simultaneously, and they are both differentiable in this interval, and therefore containing the point 0 in a deleted, I would say, the neighborhood of the point x equal to 0, and therefore the hypothesis of the theorem is satisfied, and therefore you can differentiate both numerator and denominator. The derivative of the numerator is e to the x minus e to the minus x divided by sine x. But again here, you realize that when you take the limit when x tends to 0, you get 0 over 0. Doesn't matter. You can repeat the differentiation and apply L'Hopital again, provided here that both the numerator and the denominator are both differentiable functions in any interval containing the deleted neighborhood of the point x equals 0, and that the denominator sin x does not vanish in this deleted neighborhood, and therefore you can apply your theorem and you differentiate again, and you get here when x tends to 0, this tends to 1 and this 2, so you get the limit equals to 2. Calculate the limit when here we take the limit when x tends to 0 from the right hand side. Why? Because the logarithm, we know that the logarithm, the domain, its domain are all values of x greater than 0. So you have to take the limit when x tends to 0 from the right hand side. Now the quotient here tends to minus 0 when x tends to 0. This is 0. And the logarithm of x, the ln x when x tends to 0 plus is minus infinity, so you get an expression 0 times infinity. This is an indeterminate quantity, yes indeed, but it is not one that is amenable to the application of L'Hopital. L'Hopital only applies to 0 over 0 or infinity over infinity. So what we do is that we can write it in a way which is amenable to the application of L'Hopital. You can write it in the form ln x divided by 1 over x. Now both the numerator and denominator are both differentiable in the open interval from 0 to x. And 1 over x does not vanish in this deleted neighborhood of the point x equal to 0. So now, and both they tend to 0 now simultaneously, because when you take, when they both tend to infinity, when you take the limit when x tends to 0 from the right hand side, this tends to infinity, and this tends to minus infinity. So you have now infinity over infinity, or minus infinity over infinity. So now you can apply L'Hopital. So you differentiate the ln x with respect to x, you got 1 over x, and 1 over x, the derivative of which is equal to minus x squared. When you take the limit here in any deleted neighborhood of the point x equal to 0, as if you are taking the limit of x, 1 over x, 1 over x, so you invert this quotient here, x squared by x, which is x, the limit when x tends to 0 is equal to 0, so the limit of this expression is equal to 0. Again, Here, when x tends to 0, you got what? This is a not algebraic function. You get 0 to the power 0. This is what, again, this is function 10 to 1 of the indeterminate form, 0 to the power 0. So we cannot apply L'Hopital. So what you do is that you can take the logarithm. Now, if you take the logarithm of both sides, what you get? You get the limit of ln y is equal to the limit of the logarithm. If y is equal to sine x to the power x, the logarithm of y becomes equal to x ln sine x. So you take the limit of this expression here, and then you invert, because the logarithm is a continuous function. So what you do is you can insert the limit inside the logarithm. So first of all, we have to calculate this limit. This limit, when x tends to 0, you get what? You get infinity times 0. So we have to put it in a form which is amenable to L'Hopital rule. If you put it in this form, ln sine x over 1 over x, now you can apply L'Hopital, because this you get infinity over infinity. So you differentiate here. The derivative of ln sine x is 1 over sine x times the derivative of sine, which is the cosine. This you use the chain rule we explained before, divided by 1 over minus 1 over x squared, which is the derivative of 1 over x. Here you can invert here this quotient to get the limit of x, and you can distribute the limit. Why? Because both limits exist. Here you get the limit of sine x in the denominator divided by x, and this limit is equal to 1. And the limit here, when x tends to 0, is equal to 0, so you get the limit is equal to 0. The limit of what? The limit of x, which is x ln sine x. But you need the limit of y. So what you do is that you can now, from the continuity of the logarithmic function, what you have actually calculated is the limit of ln y, but you want the limit of y. So what you do, you insert the limit. Now, and this is what you need to calculate really. You need the limit of y, which is the expression sine x to the power x, and not the limit of ln y. But the limit of 1 ln y you find equal to 0. So ln the limit of y, which is 0, now gives you the limit of y. So the limit of y, so you have ln the limit of y is equal to 0. What is the value having a ln 0? It's 1, so the limit of y is equal to 1. Here you got a quotient infinity minus infinity when x tends to 0. So what you do, you can have have equal denominator, and you can put it in a form which is 0 over 0. Again, since it's 0 over 0, you can apply L'Hopital. All you have to do is that you differentiate, and you finally obtain the limit equal to 0. Now, again, we shall speak about a property of functions. It's called intervals of increase and decrease. Now here, when a function, for example, is in the increase all the time, is increasing. In other words, when the derivative is positive, we say that the function increases. For example, this is a function which increases. How would you know that the derivative is positive? So you say that the function is increasing. For example, in economics, for example, there is something called the marginal propensity to consume. It's like, for example, it's the percentage increase in your spending. This is the increase in spending or consumption divided by the increase in income. For example, when your income increases, of course, your spending increases. And usually it's a quantity between 0 and 1. It must look like something like this. Why? Because suppose, for example, your marginal propensity to consume is equal to 0.65. It means that for every 100 cent extra money that you get as salary, for example, if it is 0.65, then you spend 0.65, you consume or you spend 65 cents and you save 35. This is what the meaning of the propensity or the marginal propensity to consume. Now, at the beginning, when your income increases, you spend more, but your needs are satisfied or saturated after a while. So what you do, although the more income you have, you keep spending, but then when your needs are saturated, your saving becomes greater, and your spending becomes, the rate of your spending lessens. So what you have here the derivative of f dash is positive, yet your second derivative is negative. Why is negative? Because you have something like this. This is called in calculus, it's called concave downwards. When your second derivative is negative. Why? Because at the beginning you spend more, and then when your needs are saturated, the rate of your spending lessens, and you have a phenomena of this sort. So this is a phenomena in which the derivative, yet it is positive, your second derivative is negative. This is, you have a constant function. When the derivative is 0, you call the function constant function, or the derivative is 0. This is when your function attenuates. It declines like this. Here, it means that your derivative is negative. When you have a function whose derivative is negative, then it means that the function decreases. Like, for example, the elasticity of demand in economics. For example, this is the percentage change in the quantity demanded divided by the change in the price. Now, the more the price is, the less the demand. And the less the price is, the greater the demand. So it's negative. It means that you have the demand decreases because the price increases. So you have the slope becomes negative. So this function here, having a negative slope, it means that the derivative is negative. But again, there are situations in which you can have a function which increases all the time, but the rate of increase diminishes. Like, for example, this one here. This is a function which increases. And this also a function which increases. But yet, f dash here increases. Is like, for example, you have, this is a distance and this is time. So the velocity is positive. But the acceleration also is positive. So the velocity increases. F dash, which is the rate of change of distance, called the velocity, increases. This is like the curve that you have just explained here. Here, the derivative is positive. So it means that your function increases all the time. But the rate, which is f dash, decreases. Here you have a higher slope, and here you have a smaller slope. Meaning that your second derivative is negative. This we call concave downwards, and this we call concave upwards. So yet both curves, you have f dash positive. It means that in both curves, the function climbs up. In both curves, yet your climbing rate here is increasing, and here your climbing rate decreases. And we can show this actually on an applet, for example. Here you have an applet here. This you have a tap which you fill in a cone, an inverted cone like this. So what you have here when you start the applet, it shows you that you fill up the cone with water. But you see here that the rate of change, of course, h increased all the time. So dh by dt is always positive. Because the function increased, or the height of your water increased. But yet, because the radius widens up, so the rate at which the height increases becomes less and less. So your second derivative is negative. It means that it starts, the height increases at a higher rate, then this rate decreases. So it means that your rate at which the height increases, although the rate is positive, yet it lessens all the time because your radius widens up. So when you watch the water filling the cone, you watch that it increases at a higher rate, and then the rate decreases. So you have the second derivative of the height with respect to time is negative, and we call this curve, the graph here, we call it concave downwards. Here we have different curves. Each of them have, here you have the curve here. As a matter of fact, instead of saying the second derivative is negative or positive, what you can do is that you watch out for the tangent. If the tangent is below the graph, then it is concave upwards. Here again, it's concave upwards because the tangent is below the graph. Whereas when you find that the tangents are above the graph, then you conclude that that your graph is concave downwards. And these are the two situations here of concavity upwards and downwards. Now, this is called a point of intersection between two regions in which the curve, here the curve, when you have the graph here, is concave downwards, and this one is concave upwards. Now, this is a point, we call this a point of inflection. The point of inflection is the point at which the graph changes, the second derivative of the graph changes sign. Here, you find that the graph here, the slope was negative, and here as well, the slope was negative. But here the slope was, let us say, for example, the slope is -3, but here it becomes -7. It lessens more and more. So you have here the second derivative with respect to x. Here it is negative, whereas here the second derivative with respect to x is positive. So you say that the graph here is concave downwards, whereas here the graph is concave upwards. So between these two regions, you have a point which we call inflection point. Actually, at this point of inflection point is the point at which f dash is minimum or maximum. And when you have a point at which isolates two regions of concavity upwards and concavity downwards, we call this point a point of inflection. Again here, the same thing. Here your graph, for example, your slope was 5, it becomes 7. So here you notice that the slope increases. In other words, y double dash is positive. Whereas here the slope was great and then it lessens. So y double dash is negative. So here the graph is concave upwards, whereas he is concave downwards. So this point here is the point of, again, a point of inflection. For example, to give you an idea, for example, suppose you have, for example, you are driving at a speed which is beyond the permissible speed limit. So what you do is that, for example, here, your speed is high. This is the distance and this is the time. And once you realize directly that there is a patrol, there is a point of inspection, and they check for the speed. So what you do, you lessen your speed. So in other words, the acceleration is negative. Here the acceleration is negative. And once you pass by the checking point, you are naughty and you start increasing your speed. So again, you have acceleration here, which is positive. So here, the rate of change of the speed, of your velocity, is called the acceleration. So here, your acceleration is negative because you lessen your speed until you pass by this checking point. And again, you increase your speed. You start to increase the speed. In other words, your acceleration is positive. So here you have this point here is the point at which your velocity is minimum. And I said before, the point of inflection is the point at which you have a local maxima or a minima for your first derivative. Here is the point at which you have the minimum speed, because your speed is high, you get a minimum of speed here, and then you start increasing the speed again. And you find that this point which isolate the two regions here you have a d double dash, or the second derivative of your distance is negative, whereas here it's positive. So we call this concave downwards and this is concave upwards, and this is the point which isolates both regions. So this becomes an inflection point. For example, study the curve y is equal to sine x in the region from 0 to 2 pi. Now, in terms of interval of increase, decrease, convexity, and concavity, what you do, because the sine x curve is simple and we've seen it before many times, so we want to know the interval. Where are the intervals at which the function increase or decrease? The interval at which the derivative is positive. When the derivative is positive, it means that the function increases. When it's negative, then it decreases. Whereas when the double derivative, the second derivative, is positive, it means that you have an interval of concavity upwards, whereas when it is negative, you have a period of concavity, interval of concavity downwards. So all you have to do in order to study this curve is by watching the sign of both f dash and f double dash. Here is your original function, which is sine x in the interval from 0, closed interval from 0 to 2 pi. In the blue here, this is the sine x. The derivative of sine is the cosine. So you get here the red graph here. This is the cosine function. And you notice directly that this curve here, f, increases from 0 to pi by 2. And it's true. Why? Because the derivative is positive here. Look here, this is the cosine. The cosine function from 0 to pi by 2 is negative. So it tells you directly that in the period from 0 to pi by 2, the function is increasing. Why? Because its derivative is positive. Whereas from pi by 2 to 3 pi by 2, your curve is going down here. So it means that your function is decreasing. To check this, you have to watch for the sign of your derivative. So the sign of your cosine function, which is the derivative of the sine, here it's negative. Look here, this is the cosine. Here the cosine from pi by 2 to 3 pi by 2 is negative, telling you that your function is going down till 3 pi by 2, because the derivative is negative. And again, since cosine function from 3 pi by 2 to 2 pi is positive, it tells you that your function is increasing. Here again, it's true. That's the sign from 3 pi by 2 to 2 pi is increasing. Whereas if you want to know the intervals of convexity and concavity, it's easy. You watch for the second derivative. Now, the second derivative of cosine is what? Is minus sine. Here is minus sine. The green here, the green curve here, is the derivative of the cosine, which is minus sine here. Look, this is inverted. It's sine which is inverted. Here, the second derivative here is negative. So since it is negative, then it means that your original function is what? It tells you that your original function is concave downwards here, and it's true. Your sine function here is concave downwards because your second derivative is negative. Whereas from pi to 2 pi, the second derivative is positive, which means that the original function is concave upwards, and it's true. Your original function here is concave upwards. So there you are. To study the convexity and concavity of your function, all you have to do is, or the intervals of which the function, in which the function increases or decreases, all you have to do is to take the derivative. If the derivative is positive, it means that your function increases. If it's negative, then it decreases. Whereas if your second derivative is positive, it means that it's concave upwards, and if your second derivative is negative, it means that it's concave downwards. And the point which isolates the two regions of concavity and convexity is a point of inflection. For example, the point at which x is equal to pi here is a point which isolates the region of concavity downwards of the original function f, and the region of concavity upwards. And actually at this point here, you have the second derivative is equal to 0. Here the second derivative, and it's equal to 0. So the point of inflection you obtain it easily. How? By you take the second derivative and you set it to 0, and you know the point. Or it's the point, and we see this later on, the point at which your second derivative does not exist. And at this point, your f dash is minimum or maximum, because here is your f dash. You see here f dash, it is minimum at the same point at which you have an inflection point. So when your f dash is like exactly the curve you saw when you are inspected at a point in your when you drive your car on a road. It was the point at which your speed was minimum, and then you start to speed up. So this point at which your speed is minimum, which is the first derivative, has a local minimum or maximum, is the same point at which you have an inflection point. And here you have an inflection point here, and your derivative is minimum. And then below this inflection point, or before it and after it, you have two regions of different nature, either concavity upwards or concavity downwards, and then again the opposite, concavity downwards or concavity upwards. And with this, we came to the end of this lecture. What we actually have explained here, we started by the L'Hopital rule, as I said, and L'Hopital rule is a very important rule. It's an easy rule that students preferred to use it, contrary to the elaborate and more tedious ways of obtaining limits using the classical methods. L'Hopital rule is a very old rule, known since the early 18th century, but it was not proved at that time. We had to wait another almost little bit than a century until a mathematician called Cauchy came and proved mean value theorem. This mean value theorem is an elaborate, more elaborate mean value theorem than the one we already seen before in our last lecture. Now, with this, we have used this mean value theorem in order to prove L'Hopital. But you have to memorize something very important, that L'Hopital rule, you cannot apply it except for two of the indeterminate quantities, because we have seen 7 indeterminate quantities. L'Hopital rule is only applicable to the two situations in which the numerator and the denominator, they both simultaneously tend to 0. So you have 0 over 0 or infinity over infinity. And for the rest 5 indeterminate quantities, you have to find a way through any algebraic manipulation, like for example logarithm, etc., to transform them into these two situations, and from there on you can apply L'Hopital rule. And this L'Hopital rule is a very efficient method to obtain limits of functions. And with this, we have come to the end of our lecture. And until we meet again, I wish to remind you, like I do every time, that all these lectures are uploaded to the site in which you can find it on the platform of the Uni Nettuno Telematic University, where you can revise them from time to time. And I thank you for your attention. And until we meet again, I'm wishing you good luck.